I'm David Thompson, and this is the next lecture in the series from the JPL-Caltech Virtual Summer School on Big Data Analytics. We've talked previously about different strategies for dimensionality reduction, including basic feature selection approaches, linear methods like principal component analysis, and also metric learning approaches which generalize linear dimensionality reduction to the case where class information is available. Now we're going to depart from the realm of linear projections altogether and move into a topic known as nonlinear dimensionality reduction. And in particular, we'll be describing kernel principal component analysis, which is a kernelized version of PCA. All right, the objectives of this talk are to first just to be able to distinguish linear from nonlinear dimensionality reduction and to know and understand the differences between them. Kernel PCA is just one of many different nonlinear dimensionality reduction strategies. I think it's a particularly useful and widespread one, so we're going to talk about that and focus on that in this talk. And you should be comfortable with it and its derivation, and also have some familiarity with the other methods that are out there and available to you if you prefer to use those for other applications. More generally, there are advantages and pitfalls to nonlinear as opposed to linear approaches, and we should try and understand those too. All right, so why do we care about nonlinear projections? Well, there are some cases where linear subspaces just aren't good enough. I mentioned before that linear subspaces are almost always useful on any data set, but they may not adequately represent the underlying manifold, which may have some other nonlinear structure, right? So even if I start and I'm able to project my data linearly down to, say, 20 or 40 dimensions, I still might be able to find a more efficient representation that captures that models the data even better using a lower dimensional manifold. And that's the idea behind nonlinear dimensionality reduction. So here's an example here portrayed in these four image panes. We have in the upper the upper left, this S curve, which is a curved manifold. It's a two-dimensional surface that's embedded in a three-dimensional space. Now, if you were to do a linear dimensionality reduction on this data set, that would amount to maybe taking a hyperplane somewhere through that data and projecting all the points onto that hyperplane. Now, try as you might, you're not going to be able to find a single hyperplane that would let you recover the original points of those data. No matter how you orient that hyperplane, you're always going to lose quite a bit of information. And this is reflected by the PCA projection result that you see there in the upper right, where it tends to mix a lot of unlike colors together, even though the different colors are supposed to be on different sides of the manifold. So the PCA projection down to 2D is really inadequate, even though this structure is intrinsically two-dimensional. We can't capture that with a linear projection. The other two panels in the bottom show different nonlinear dimensionality reduction methods, and they actually are capable of modeling and unfolding this manifold in order to represent the data adequately. And that's what nonlinear dimensionality reduction strategies are all about. So some other examples of that. Here is a case using image data. We have just two axes of variation here. We're looking at a face from different angles. And so the left-right pose is one axis of variation, and the up-down pose is another. Note that any two of these data points that are close to each other in this manifold are also going to be similar to each other. So it captures sort of the local structure around all data points, and it also captures the global structure that there are these two main axes of variation. But it's a highly nonlinear relationship, naturally. And if you were to try and embed this in the space of pixel attributes, you'd get some highly folded structure probably, even though the manifold itself is continuous, right? Because you could continuously move this camera around and get practically no change between neighboring data points. So the local structure is smooth and continuous, but of course it's a very complicated manifold. And this is from early work in ISOMAP in order to identify structures using nonlinear dimensionality reduction. Here's another result from the same paper. This is looking at handwritten digit recognition. So here we have lots of examples of twos, and you can imagine that these twos live on a manifold of different different manifestations of what a handwritten 2 should look like, right? So if you change any one of these just a little bit, you move along the manifold to its neighbors, right? You're still on the manifold as long as it's still a valid 2. And this just emphasizes the fact that these manifolds needn't fill the space. They aren't always rectangular sheets. You can have spikes and pseudopods that jut out, like you see down there in the lower right. There's a sort of a spike in this distribution representing the 2's with the curly Q's on the top. But that said, we can still sort of arbitrarily ascribe different English titles to these axes. Here they've been called the bottom loop articulation and the top arch articulation axes. But really all we're trying to do is come up with some nonlinear structure to describe the universe of possible 2's, right, which is a highly nonlinear manifold in the original space. How do we represent this structure? Well, one way we can do this, there are lots of different ways. A lot of different nonlinear dimensionality reduction methods involve looking at graphs, for instance, to find local neighborhoods on graphs. But kernel principal component analysis, which is the one we're going to be exploring most deeply in this talk, relies on the intuition that many data sets which are not linearly separable in their original attributes can be made linearly separable by projecting them into a higher dimensional space. That is, we can add attributes which are simple arithmetic operations of the original attribute space, which cause the data to become linearly separable in that new feature space. So here's an example where we have 2 data points. This bullseye data cloud has 2 classes. The red and the green, which are not linearly separable. Try as you might, you cannot draw a separating discriminant line through that, or separating decision boundary through that data cloud. However, when you add a third feature to the data set, which is the sum of squared attributes, then the result becomes linearly separable that you can see here in this 3-dimensional portrayal. So we're mapping this into a high dimensional space where linear relationships are sufficient. If you were to map that decision boundary that you'd make in this higher dimensional space back into the lower dimensional space, you'd get a nonlinear decision boundary. So we can actually use all of the tools from our linear analysis toolkit in the high dimensional space and get nonlinear results in the original space. This is an important insight, important intuition, and is really the foundation of kernel principal component analysis. So what does this look like for KPCA? Kernel PCA takes our training data, it maps it into some higher dimensional feature space where we perform principal component analysis, right? Which in the original data space, it would be represented as a nonlinear projection, right? A nonlinear transformation of the data. If we get some new data point, then we can similarly project it into our higher dimensional feature space and find its low D representation in that new high dimensional feature space that's with projections that have been learned from our training data, right? So this is the intuition behind KPCA. But you might say, well, this is fine, but it's kind of contrary to the whole point of dimensionality reduction, right? If we're creating these arbitrary new high-dimensional feature spaces, doesn't that actually increase rather than reduce the dimensions? It's true, it would, except we also have the benefit that for KPCA, you don't actually have to do any calculations in the high-dimensional feature space, and I'll describe that in a moment. The derivation of kernel PCA follows our PCA. So we now take some mapping of the original data set, which is phi. So phi of x sub I is the mapped data point in this high dimensional space, and we envision some projection in this high dimensional space that's here represented by the set of orthonormal basis vectors in the matrix U, right? And the expression here, U times U transpose times phi of x sub I, gives us the reconstruction of the data point, phi of x sub I, after down projecting it through this linear basis, right? And so we subtract the original data point in the high dimensional feature space from its reconstruction in that high dimensional feature space, and we get an error score, right? So we're trying to minimize reconstruction error in this high dimensional space. Note that for this expression, it's actually important that the data set phi be centered. Similarly to regular PCA, where we're working with zero mean data, we had to subtract the mean off first. Here as well, we're going to be working with data that's centered in the high dimensional space. All right, so this is equivalent. I mentioned previously the relationship between singular value decomposition and PCA. So the same thing applies here. We can actually do a singular value decomposition of the high dimensional features or the high-dimensional data set phi sub x, and then that gives us our basis vectors u. So we define u to be the left singular vectors of phi sub x, right, associated with the highest singular values in this matrix of singular values sigma. All right, so equivalently, right, just as in our previous PCA example where there's an equivalence between SVD and calculating the eigenvectors of the covariance matrix, the sample covariance matrix, we can calculate the eigenvectors of the sample covariance matrix of phi sub x, which is a bunch of dot products essentially. And again, this has to be the eigenvectors of the centered matrix, as in PCA. Okay, this brings me to the kernel trick. So as before, we can work with this, as before, PCA relies on the eigenvectors of the sample covariance matrix, x times x transpose, and we can represent that in the projected space by a matrix of dot products, right? And the expression for that is given here. So what this means is that we can implicitly model any nonlinear transformation, phi of x. The only requirement is that we have to be able to calculate dot products between those data points efficiently. We can, as long as we know the dot products, we can figure out what the projected representation is. So we actually never have to calculate the explicit high-dimensional representation of the new feature space. So that typically the way this is done in kernel methods, this is known as the kernel trick, is to come up with a kernel matrix of dot products between all the different data points. And so we describe here the dot product using a kernel function k, which represents point similarity in this high-dimensional space, or similarity in the attribute space, which equates to their dot product, right? So this is different. This is slightly different than PCA, whereas PCA has a covariance matrix that's scaled with the number of input dimensions n. Here we're working in KPCA with this kernel matrix that has dimensions similar, that's dimensioned according to the size of our data set, right? Because we're calculating the dot product of all data points against all the others. So this scales with d, the number of data points in our training set. What kernel function should we use? How do we calculate these dot products? Well, a common method is to just look at some sort of decreasing function of distance in the original feature space, right? Typical choice is the Gaussian kernel. We introduced this way back in the first lecture, right, as a way to describe locality between data points. That it has a width parameter h that we can set using cross-validation if we like. And this falls off rapidly as distance increases. So we can apply this to pairwise to all of the different data points and figure out what their dot products are in this high-dimensional space. So we're ascribing a functional form to their dot products, which lets us calculate this nonlinear projection. Okay, so there's a catch. I mentioned before that our data set has to be centered in this high-dimensional feature representation, that it has to be zero mean. And this won't be the case for a general kernel matrix that we derive. What this really means is that we want to come up with some some data point, some projected data point, we'll call this phi tilde of x sub I, which is the original phi of x sub I minus the mean of all of the phis. And you can actually push this through some algebra to figure out what its implications would be for the kernel matrix as a whole. So with the kernel matrix elements defined as the dot products of our phi of x sub I and x sub j, we then perform that substitution from the top line, and it actually works out to some simple arithmetic operations on the kernel matrix that perform this centering operation. So I won't walk you through the gory details, but it basically amounts to this operation that we have to perform on the kernel matrix after calculating the kernel function at all data points in order to center it before we can do SVD. All right, so here's from beginning to end, the recipe for kernel principal component analysis. First thing to do is pick a kernel function. I hardly recommend we start with the Gaussian. There are lots of other kernel functions and a whole literature devoted to defining different kernel functions for different kinds of input spaces. So I encourage you to look into that if it's a topic that interests you. After you have a kernel function, you can calculate the kernel matrix and then center it according to that expression that I showed you before. Here I've written it out in matrix notation with the ones indicating just a matrix with entries of 1 over d, where d is the number of data points, right? So it's a fairly straightforward centering operation, and then you solve the eigen problem, which is, again, this eigensystem based on the kernel matrix, which gives us our projections alpha. And then alpha is, of course, the size of all of our data points in the training set. So in order to find the projection of a new data point, we multiply the alpha by its kernel evaluation for all of the data points in the training data with respect to the query point that we're trying to project. And that gives us the location along some new dimension for the projected data point. Okay, so here's an example of what it looks like in practice. So we've taken the face data set and down projected it with PCA first. So this is a purely linear projection of that face data set before. This is courtesy Gaussian in 2006. You'll note that there are lots of places where neighboring faces have actually, or neighboring points in this data set have actually very different images, right? So this doesn't necessarily do a good job of capturing the underlying structure. We can do better with KPCA. Now, this isn't a perfect unfolding of the manifold, right? It doesn't totally fill the space with a beautiful rectangle, right? But that's that rarely happens in practice, actually. And this is actually a pretty good result in that neighboring data points also represent similar images, as you can see from the examples that are plotted. So this actually does a much better job for this face data set than a purely linear projection would, as long as we're working with just 2 dimensions. So Kernel PCA nonlinear dimensionality reduction is a more efficient method in this case of representing the data. Other methods for nonlinear dimensionality reduction, and indeed there are a bunch. Kernel PCA is a common one, but there are lots of others based on graph structure, like I mentioned. Laplacian Eigenmaps are an example of that. It's a sort of local linear embedding is another case. Isomap is a famous algorithm that's been around for over a decade now. Multidimensional scaling is a classic algorithm that takes a matrix of affinities, which in some ways is similar to the kernel matrix that I described before, and creates a low-dimensional projection that preserves those affinity values, those distance values. Feed-forward autoencoders are kind of an exotic approach that's actually gained a lot of traction of late in the deep learning community. So this is based on neural network modeling, and again, that's something that I encourage you to investigate further if neural networks are of interest. Feed-forward autoencoders can be used to perform nonlinear dimensionality reduction, irrespective of the ultimate classification goal of the neural network. All right, and of course there are many more strategies and a huge literature on nonlinear dimensionality reduction, but I hope I've given you a pretty good taste with this lecture. Okay, so one note in closing, nonlinear dimensionality reduction doesn't always work better than the linear case. It does work well when you have a lot of data, when you can fill the manifold and you don't have a lot of gaps or outliers. It works pretty well when the intrinsic dimensionality is relatively low and your data is pretty evenly distributed on the manifold. If you don't have a lot of data, then some simpler structure is generally going to give you better results. Occasionally, nonlinear dimensionality reduction strategies can give you degenerate solutions, or they can be unstable, and this is just goes with the territory. When you have a more flexible model, right, you need more data in order to fit it adequately. So this is just a general caveat to keep in mind. I would always start with linear dimensionality reduction strategies to see if they're sufficient for your classification or visualization task, and only pull out nonlinear dimensionality reduction when it turns out to be absolutely necessary. It's particularly helpful in a lot of cases like image data, where you have smooth transitions, right, from one frame to the next, or in pose estimation, where you have, like, say, an articulated body that's moving and can define relatively simple low-dimensional manifolds in that space, consisting of different poses and joint limb articulations. So there are some sort of cottage industries where these nonlinear representations have become really useful. But if you have some brand new data set, then start with the linear. Okay, so in summary, methods like kernel principal component analysis can find nonlinear structures by projecting data into higher dimensional spaces and then applying the same linear toolkit from PCA in those implicit spaces. And you can avoid the cost of this calculation with the kernel trick, that is computations based on dot products, which are represented by a kernel function that you can define.